Hello, ladies and gentlefolk, and welcome to the virtual lecture on 10.7. This lecture is going to focus on thin convex lenses. That's really what you need to know about. However, for a greater understanding of all different types of lenses, I highly encourage you to check out the supplementary reading or any of the other links on the website. But let's go ahead and venture on to talk about thin convex lenses. Specifically, these types of lenses are most important for glasses, for cameras, for how your eye works. They're called converging lenses. We're going to talk about why that's the case. But these are the type of lenses that are most applicable to technologies and to human physiology today. Our objectives today: describe how an image is formed by a thin convex lens, determine the location of image formation for a thin convex lens, determine the magnification of an image for a thin convex lens, determine whether or not an image is upright or inverted for a thin convex lens, and determine whether an image is real or virtual, again for that thin convex lens. So I've been saying thin convex lens a lot. Let's first and foremost define what that is. So the word convex itself means to be bending outward. So a thin convex lens is just a biconvex lens, or a lens that has two convex sides. In other words, both of its sides are bending outward, just like the picture shows. And the great thing about these types of lenses is that when light rays go through these lenses, because the glass is curved, those rays are refracted and allow a real image to form on the other side. So a very important part of your thin convex lens is something called the focal point. So I just talked about how your light rays, once they come into the lens, will all refract and hit a single point. That point where all of your light rays intersect is called the focal point, and the distance from the center of that convex lens to the point where all of those rays converge is called the focal length. I'm going to talk a lot about focal points and focal lengths. So if you're forgetting what that is, just flip back to this slide. So now let's talk about how these thin convex lenses are used to create images or to modify images. All right? And this is obviously important because we need a magnifying glass to magnify things. We need a microscope to be able to look at small, tiny organisms. We need telescopes to see the stars. All of these things come from largely thin convex lenses. So when scientists are coming up with these great technologies, those scientists ask three really important questions. Is when you are looking at an object through a thin convex lens, 1, where will the image of that object form? 2, is the image upright or inverted? And inverted just means upside down. And 3, is the image larger or smaller than the actual object? All right, so those are the three questions to keep in mind, and those are the three questions we're going to focus our investigation of thin convex lenses on today. So we talked in class on Monday about ray diagrams for plane mirrors. Thin convex lenses also utilized ray diagrams to predict how an image of an object will form and where exactly you'll see that image at. So let's say that we have an object. Here it's just drawn as an arrow, but that object could really be anything from a tree to a planet. And there are 3 different rays that we are going to be using to predict where the image of this object will form on the other side of that lens. Those 3 rays, all right, one is a ray straight from the top of that object onto the center of the lens. One goes from the top of the object through the center of the lens. And the last ray goes from the top of the object through the focal length. So again, that focal length is where all those rays converge. It's very, very important because that'll help us figure out where this image forms. So on the opposite side of the lens, we draw 3 more rays. So that ray that you originally drew going from the top of the object to the center of the lens is going to go now through the focal length on the opposite side of your lens. that second ray that you drew from the top of the object straight through the center of the lens will just continue going straight. It's not refracted. That third ray that you drew going through the focal length on the side of the object is now going to come out straight on the other side. That's how those rays would end up getting refracted. That green dot is the point of intersection for those three rays, and that is where the image will form. And that image, you'll notice, is smaller. So unlike plane mirrors, with lenses, our images are not necessarily going to be the same size as the object. This is why lenses are so helpful to us for correcting vision, helping make objects look larger or smaller, and in magnification, things like cameras or glasses or telescopes, microscopes, anything. All right? And it's also important to notice, like I said, we indicated those objects with arrows, but really it could be trees, it could be anything. It's not just limited to an arrow. Okay. Now, I highly encourage you guys to get practice on your own, to check out the PhET Virtual Lab on the course website. We are going to get practice drawing ray diagrams. You'll get practice seeing exactly how these images are formed in the lab in class on Thursday. But for extra practice right now, that PhET Virtual Lab will actually allow you to slide objects, so you can actually see how the size of the image changes as you move the location of where that object is with respect to the lens. That being said, there are two very special cases that I do want to talk about for thin convex lenses. Most of your images will form, those rays will converge to a single point, and you'll have a beautiful image just like we saw in that first example. This is an example, however, where we draw our three rays, but you'll notice the object is in front of the focal point, and so our ray going from the focal point to the object to the lens is way, way off. It's much farther away than the other two rays. And furthermore, you'll notice that the two rays, the one going straight and then through the focal point on the other side, and then the one going straight through the origin or the center of the lens, they're actually diverging. So they're getting farther apart as opposed to getting closer together. So we're sitting here and we're like, wait a minute, no image must be forming. And that's actually correct. What's happening is that no real image is forming. But just like we talked about virtual images, we actually can see a virtual image in this case, just like we could with mirrors. And so the way you figure out where that virtual image will form, you just backtrack all of the lines that you would have drawn on the other side. And so I take the extensions of my three rays, and the intersection point you'll actually notice is behind the object in the case. Furthermore, you'll notice that it's upright. It's not inverted. So any real image that forms on the opposite side of the lens is actually going to be upside down. Whereas if you see a virtual image, this image will be upright and it will be magnified and on the same side of the lens. Okay. A last case to note is that for objects located exactly at the focal point, no image will form. And the reason for that is because all of your refracted rays will actually be parallel to one another. So those rays will actually never converge. You'll never be able to see an image, real or virtual in that case. So that being said, let's talk about the 5 cases that you can have with thin convex lenses. First, you can have an instance where your image is real, which means that an image actually forms. You can actually see a picture on the other side of that lens. It's inverted, which means it's upside down, and it's smaller. And that happens when your, not image, I don't know why I wrote image here, but your object, when your object is located beyond 2 times your focal length. If you have an image located at exactly double the focal length for that not an image, an object, sorry. If you have an object located exactly at 2 times the focal length, then you will again have a real image. It will still be inverted, so it'll still be upside down, but it'll be same size as your original object. Next, if you have an object, not an image, an object located between your focal length and double your focal length, you'll still have your real image, but it'll be inverted upside down. It'll also be significantly larger than your original object. Again, we talked about if you have an image, or not an image, an object located exactly at your focal length, no image will form because all the refracted rays will be parallel to one another. And then finally, if you have an object located closer to the lens than the focal length, you'll have this virtual image. It'll be upright and it will also be magnified. This is important to know because you'll notice, wait a minute, why are all of these images upside down for when you have an object located beyond the focal length? And the reason for that is because that's just how the images form. When the rays get refracted, you actually flip your image. So why is it that when you look through a camera, why is it that when you look through glasses, why is it when you actually are using your vision, you see things straight up? And the reason for that, one, is your eye does a really, really cool thing. The images that your eye actually sees are in fact upside down, but your brain turns them right side up. So one, that's a really cool thing. And two is when you're dealing with cameras or microscopes or telescopes, for example, a lot of times they'll have something called a 2 convex lens structure, which means that those images are actually magnified through 2 of these thin convex lenses. So they are turned upside down and then they're turned right back up again. So fun facts for you there. So now that we've talked about the 5 cases that you can have, now that we've talked about how to draw ray diagrams, I want you to check yourself. Go ahead, pause the video. If you need to draw this, by all means, go ahead. And for each of these 8 objects, I want you to draw where those images were formed, and also note, are they going to be real, virtual, inverted, upright, magnified, or smaller? So go ahead, pause the video now. All right, this is how your answer key should look. I did not include all of the ray diagrams for each of these individual objects because then this answer would just look completely convoluted. However, please go back if you did not get your images to appear like these answers. Please go back, re-watch this portion of the video, check to make sure you really understand how to draw these ray diagrams and exactly how these images should look. Just to let you guys know, images 1 through 5, those are those inverted real images, and images 7 and 8 are upright, magnified, and virtual images. So now that we've talked about how images form, how we can predict where they'll form and what generally they'll look like with relationship to the original object, now let's talk about actual math. How do scientists and engineers actually know how much of a curve to give your glasses to magnify objects a certain degree? Or how do scientists and engineers know how to focus their camera so that it'll focus on a certain object at a certain length? And that has to do with these 2 wonderful equations. The first equation is used to help us predict where the image will actually be located. So as you notice on the diagram, the DO is the distance from the lens to the object. The DI is the distance from the lens to the image on the opposite side of the lens. And F is the absolute value of the distance from the lens to the focal length. The equation below talks about magnification. So M stands for magnification, all right? And it's really the height of the original image divided by the height of the object. So it's the ratio of the heights of the image and the object. And that's equal to the opposite of the ratio between the distance from the image and the distance of the object. Excuse me. And And as you guys may have noticed, is that the closer your object is to the lens, the farther the image gets away from the lens, and also the larger it gets. So that's how those equations work out. So now let's see them in action. Before we do that, I take that back. I do want to talk about what a positive or a negative sign will mean for these things. So we talked about virtual and real, upright and inverted. So first is you can have a negative DI, or a negative distance to the image. All that means is that the image forms on the same side of the lens as the object. That's that virtual image. If your HI, or the height of your image, or the magnification is negative, that just means that you have a real image. It's inverted. It's just upside down. Okay? Let's go ahead and see this in action. So here's an example problem where we have a 4 centimeter tall light bulb. It's placed a distance of 45.7 centimeters from a double convex lens having a focal length of 15.2 centimeters. Determine the image distance and the image size. I want to let you guys know a trick is that because all of these things are ratios, you don't actually have to convert centimeters to meters in this case. So everything you can leave in centimeters, that's fine. Just make sure your answer is also in centimeters and that all of your distances are in the same units. So for example, if we had 4 meters and 45.7 centimeters, we would have to convert one of those. Okay? So because this problem asks for 2 things, both the image distance and the image size, I've created 2 separate problems for you. Let's solve the image distance first. And the reason I'm always going to do that is because I need to know my image distance before I can solve for my image size. The first thing that I do is I plug in my distance from the lens to the object, and I plug in my focal length into my first equation. I then go ahead, I subtract the 1 over 47.5 from both sides to get 1 over the distance to the image by itself. And I get 1 over the distance to the image to be 0.0439. And just like when we had equivalent resistances for parallel circuits, we have to take 1 over or flip that final answer. So we get the distance to the image is in fact 22.8 centimeters. Because that's positive, I know that my image will form on the opposite side of the lens as my original object, and so it will in fact be a real image. Now let's look at the image size. So in this case, I'm not solving for magnification, so I can just leave that M off and just look at the height of the image versus the height of the original object. So what I'm going to do is I'm going to go ahead and I will plug in my height of my original object, 4 centimeters from my original problem, plug in that 22.8 I solved for in the previous part, and that 45.7. Go ahead and multiply by 4 on both sides, and I get the height of my image to just be negative 1.99 centimeters. And this is, in fact, what I expect because I expect, since I already know this is a real image, it to be negative height because I know it's inverted. This is also a great way to check yourself because I can already look at the distances. The distance of my object is 45 centimeters from the lens. That is more than double my focal length. So my focal length is 15.2. Double would be 30.4. So 45.7 is greater than that. And so because I know that I'm more than double the focal length away from my lens, I should have a real image that is inverted and smaller than my original. And it's great that my math works out. Now I'd like you to try a problem on your own. Pause the video now, read the problem, and then go ahead and try to solve it. Play the video again when you're done. Here's your answer. Go ahead, check your work. Ultimately, you should have gotten that this is a virtual image that is 18.3 centimeters away from the lens on the same side of the object. It is upright because my height is positive, and it is larger than my original image at 8.81 centimeters. Going back to my objectives, we've covered everything. I know that this was a jam-packed lecture, so if you're still confused on any of these objectives, please go back. Feel free to replay the video and rework those problems. And if you still want to know more, we didn't talk about how the eye works. We didn't talk about how telescopes work exactly. So if you're interested in those things, there's some extra resources on the website for you to fuel your curiosity. Thank you guys and have a great night.